Alright, chemistry. Here we go. As I try not to break the things on my desk. No, we're good. Everything's fine. It's very under control. I apologize if the sound, the mic pickup is a little different. I'm working on some stuff, trying to figure out how to make things sound less clickety-clacky. In any case, let me pick up right where I left off here on page 20. And let's go through these counting examples, right? Just counting. So, if I zoom in a little bit, just to see things a little easier. That's better. Alright. So in this first one, I should count... Oh my goodness. That is... Alright, I'm finally gonna... We're going to a smaller. So I have 1 beryllium. I have 2 oxygen. I have 2 hydrogen. Right, because again, this 2 distributes to both of those elements. Number 3, it's 1 nitrogen and 2 oxygen. Boring, boring, boring. This one is slightly more difficult. I have 2 aluminum, 3 sulfur, and 12 oxygen. And the reason for that, again, is the distribution, right? It's 3 times 1 and 3 times 4. So I have 1 nitrogen, 4 hydrogen, another 1 nitrogen. Now you could have just said 2 nitrogen and been fine, and 3 oxygen. The reason these nitrogens are separated from each other is because they exist in different polyatomic ions. And remember, polyatomic ions have to act as a group, so they're going to stick together. You can't separate the pieces of the polyatomic ion unless you go through a whole lot of trouble. So they're going to stay together. This is 2 sulfur and 2 fluorine. It's fluorine, not fluorine, just for the record. Here I have 2 sodium. Na is sodium. I have 1 carbon. And I have 3 oxygen. Finally down here, 1 carbon and 4 hydrogens. Right, so just counting. Counting should be fine. The only thing to be careful of is something like this, where you have parentheses, know that you need to distribute, just like you would in math class. Alright. What we're going to do is we're going to kind of continue to move forward. Alright, so we've talked about atoms, talked about putting them together to form molecules, specifically to form compounds. Compounds are neutral objects. They are substances because they are exact, right? It has to be like H2O is exactly water. I can't change that. Now we're going to classify them. But before we classify them, what I need to do is take a look at the reference table. Ta-da! The reference table. Alright. Now here's the deal. Right here, you should notice this bold line that zigzags. Looks a little bit like a staircase. So we call it a staircase. So here is the staircase. All the elements to the left of the staircase, except for hydrogen. But all these elements over here, these guys that are way to the left of the staircase, and these guys that are just to the left of the staircase, they are metals. Things like zinc, and copper, and nickel, iron, gold, silver, right? They're all metals. To the right of the staircase, you should see far fewer elements. Additionally, helium and hydrogen actually counts here. So hydrogen really belongs with these characters on the right. They are nonmetals. Right? So nitrogen, oxygen, chlorine, these are nonmetals. Any element that has a side that's touching the staircase, we generally call metalloids. They can act as metals or nonmetals depending on what you choose to combine them with, what you put them in a compound with. There is a single notable exception. This element right here you know very well. It is aluminum. It is touching the staircase. It is not a metalloid. it is definitely a metal. The prime example for metalloids that they love to use is right here. It's number 14. It's silicon. Right? Silicon can be used in computer chips. It can be superconductive. Silicon can also be used to make like a rubber type substance, right? For like gloves or cooking utensils, you can make like silicon cooking utensils, which are very clearly non-metallic and non-conductive. So that's like the prime example because it can be both, it can act like a metal or it could act like a non-metal. It depends on what you combine it with, right? The reason I needed to do that was because back on page 20, I think this is page 20. This is page 21. Back on page 21 here, we're talking about ionic compounds. These are compounds that contain a metal. These are elements located to the left of the staircase, not including H. And a nonmetal. So if it has a metal, something on the left, a nonmetal, something on the right, we call it an ionic compound. All right, that's too small for this. Let's do that. Wait, can I just adjust? Where? No. Okay, I think I have to do that. So we call it. What if I? Oh, that is better. An ionic compound. Alternatively, if you have a compound that contains a polyatomic ion, it's also an ionic compound. So if you can play Where's Waldo with table E from your reference table, page 2, and you can identify that it has a polyatomic ion, then it must be an ionic compound. Now we call them ionic because they have both positive and negative ions. So there's some plus stuff and some minus stuff. The negative ion is your nonmetal, so it's kind of nice. You have that alliteration again. While the positive ion is the metal part. So NaCl. Na is on the left side, Cl is on the right side. That's a metal and a nonmetal, so it's an ionic compound. Additionally, because it contains exactly 2 atoms, we call it a binary compound. So NaCl is a good example of an ionic compound. It's also their best example of a binary compound. Nope, not what I wanted to do. I wanted to scroll down. I guess I have to do this. Okay. Next we have molecular. You might also see the word covalent. They mean the same thing, and in fact you'll see it in the very definition. A compound that contains only nonmetals is a molecular or a covalent compound. We call them molecular compounds because they exist of individual molecules. So C2H6, carbon and hydrogen, are both nonmetals. It's a molecular compound, It has 2 carbons and 6 hydrogens. Nothing tricky there. Now, empirical formulas. I'm going to put a little star next to this. It's a very specific topic for a very specific question. It has shown up like every year, so this is why we continue to do it. If you choose to take more science in the future, you will do more with empirical formulas. The only thing that we are going to do is that empirical formulas are the smallest whole number ratio of elements. So N2O4, if you look at this, I'll go back to my small one. This 2 and this 4, right? You can divide both of them by 2, and you end up getting this, right? NO2, that's N1O2, right? So I took those numbers and I reduced them down. Take the greatest common factor, divide by it, and you can get it to reduce. Now, you should notice that the empirical formula does not need to be related in any way to the molecular formula or the real formula, the actual formula. N2O4 is still the molecular formula for that compound, but if you're asked what is the empirical formula for N2O4, you need to take the numbers and reduce them down as far as possible. If you had to do the empirical formula for something like, C2H6, I can divide both of these by 2, that would become CH3. Right? Empirical formula is take the numbers, reduce them down as far as possible. All right, now that we can talk a little bit about making compounds, identifying compounds, sorry, but we need to be able to make compounds. The big deal is that all compounds are electrically neutral, which means they have no charge. So you're not going to see something like at the bottom of the page there, down there, that way. You have the Mg plus 2 and the F minus 1. I need to combine those in order to make it a neutral object. So, I'm going to zoom way, I'm trying to zoom way in here. Alright. So Mg plus 2 and F minus 1. Now, in order to balance out charges here, I need to make sure that the amount of charge, the amount of positive charge that I have and the amount of negative charge that I have completely cancel each other out, and right now they do not. If I just took one of the Mg plus 2s and one of the F minus 1s and I slapped them together, I would not have something that was neutral. I would need... Oh my goodness. Why is... Oh, I know why. I zoomed in. That's my fault. I did this to me. If I have an Mg with a plus 2 and an F with a minus 1, that's not enough. I need 2 of these. I need 2 Fs. Right. So, I need to write a formula that represents that I have 1 Mg and 2 Fs. That means it's going to be Mg F2. There are a couple other ways to do this. Another way that I would do this is that if I know that I need to take these two things and make a compound out of them, I would just smash the two symbols together and then figure out how many of each do I need to balance this. Well, I would need 1 of these and 2 of these, so I could do that again. Right. There is a small shortcut that you can take. When you are taking these charges, and let me move this up a little bit just so that it's a little easier to see. So Mg F2. Another way you can come to that conclusion. Take the 2 ions, take the symbols and just slap them together. Positive one first, negative one second. Take this number and put it down here as a subscript for the second. Take this number, put it down here as a subscript for the first. Just the number, not the sign, right? So it's a way to check yourself. There's 1 Mg, there are 2 Fs. That's exactly what we found. Much of the time, 98% of the time, this shortcut works. So if I want to, what I'd like you to do very quickly, right? Pause the video, well, try to do number 2 and number 3. You'll find things that are very familiar to you. Pause the video for a second. Do those 2. Then I'm going to explain these guys a little bit. Guessing you're back. If I combine H... Just kidding. If I combine H and O with a minus 2, I should get H2O. Over here, I will end up with NaCl. Again, just trying to balance out the charges. Now here, if I just put these guys together, again, that's not enough, but I can do this trick. This 1 goes down here. I don't really need to write 1s. This 3 comes down here. This tells me I have 3 lithiums. 3 times plus 1 is plus 3. I have the minus 3. They cancel each other out. Right. This last example, if you remember, back here on... oh gosh, what's happening? If you remember back here on page 20, where you have these parentheses and then the subscript, well, that's what we're about to do here in number 5. Here in number 5, I have to combine Al and CO3, and if I take this number and put it down here, I get Al2. If I take this number and put it down 3, I get 3, and now it looks like I have Al2CO33. And that's no good, because I don't want to say that I have 33 oxygens. I want to say that I have 3 of this. And in order to say that, I put parentheses around the polyatomic ion. Right? Parentheses around the polyatomic ion means that all the stuff that all that whole polyatomic ion, I have that many subscript of them. So I have 3 of that polyatomic ion. And if I look at this, what this means, it means that I have 2 plus 3s. Well, that's a plus 6. And I have 3 minus 2s. Well, it's a minus 6. So I got a plus 6, I got a minus 6. That all cancels out, right? Now, this was how to make a compound from the ions. What we're going to do next is we're going to take the compound, take ions and make a compound. So from the ions form a compound. What we're going to do next is we're going to take these compounds and we're going to figure out what ions are they made of. Alright? Now, I'm going to make a separate video because I hit my 15-minute limit here. I'm a little over it, but that's okay. Make a separate video. I'll just start this up, a new one. This, right, this explanation, I'm going to do some examples first, and then I want y'all to try these. But I'm going to talk you through this, alright? Coming back soon.